Hello, everyone. Welcome to the talk this afternoon. It's my great pleasure to introduce Professor Nikolai Moshchevitin from Lomonosov Moscow State University. His talk today will be on some open problems in Diophantine approximation.
Oh, thank you very much. Thank you very much. It is a great pleasure and great honor to me to speak during here during the Congress in Beijing. So, what I can say first, our section is called analytic number theory, but I'm more involved in Diophantine approximation and geometry of numbers. And in my opinion, maybe here we have more geometry than numbers. But nevertheless, I decided to add some analytics into my talk also. I want to speak about some maybe not very popular and not very well known, but very special and particular problems in the Diophantine approximation. I mean, open problems. Of course, there is a lot of very well famous open problems in the Diophantine approximation and generally speaking in number theory. So at my next slide, at my next slide, I would like to mention three of them. So, but well, I will not speak about these problems. So I just mentioned, I even did not write here what is Riemann hypothesis because everybody knows. As for Diophantine approximation, I think the most famous problem is Littlewood conjecture. So if you have two real numbers and you deal with this, for me, this sign is distance to the nearest integer. Here is the explanation. Here is, it doesn't look, okay, it doesn't matter. So here is an explanation. So if you consider this product of three linear forms, then for any numbers, alpha and beta, it is, infimum is zero. It is a very famous problem. A lot of people worked on it. So, and a lot of words said in accordance with this problem. There are interesting results, interesting conjecture by Castle, and Dyer, Margulis, and others. I will not speak about this. Probably people know the Zaremba conjecture, which became popular. It was known long ago. I think it goes back to Korobov, who formulated it probably earlier than Zaremba in 50s, or even maybe to Edmund Glavka. But in last decades, it became popular because of a fundamental paper by Bourgain and Kantarovich. And I think this is also, maybe it is not as known as Riemann hypothesis, but now this problem is popular and people do know it. So the statement is that for any denominator, you can find a numerator such that if we consider or coprime to the denominator, if we consider ordinary continued fraction expansion, then all the partial quotients will be bounded by 5. This conjecture has wonderful computational evidence because it is very easy to decompose a rational number into continued fraction by computer. This is Euclidean algorithm. But still, it is very far from the solution. So the famous Korobov's bound, it is easy, and it is in 50s, says that instead of this 5, we can put that it is less than log q. let it be prime. And quite recently, there is a progress, and it turned out that I was also a little bit involved in this progress. This is Murphy, Shkredov, and me. I don't know why, by the way, I don't know why I'm the author here. So this bj is less than log q over log q. So there is a recent progress. But it is related to additive combinatorics, to non-commutative combinatorics. Okay, but these very important problems, which I will not speak about, I want to speak about easier, simpler, and much less known problems. And it seems to me that this is important because, for instance, in particular here, there is a lot of young people, and to solve problems, you should be young, and then you have some opportunities. So I will follow the ideas of the famous paper by Wolfgang Schmidt, where he formulated several open problems, which are, for instance, much easier than Riemann hypothesis or Littlewood conjectures. For instance, Schmidt, in his paper, mentioned a lot of these problems, Schmidt's problems were solved. Mentioned, for instance, so-called bad conjecture, which lead to weighted approximations. I will say a few words at the very end. Behavior of minimus of parameter families of lattice. This conjecture also was solved. Now it leads to parametric geometry of numbers. Parametric geometry, which is now very popular. Fractional parts of polynomials. The most famous is alpha n square. The famous result by Zakharescu, which claims that such inequality has infinitely many solutions, appeared after Schmidt pointed out these problems and some other problems. Following Schmidt a few years ago, I decided also to write a paper devoted to open problems. It was more than 10 years ago. Some of them were solved now. Some of them are not, still are not. So some of my problems, which I will speak about today, you can find in this preprint, but not all the problems, just some of them. Okay, now I am continuing, and I will speak about 6 particular problems. Here is the plan of my lecture. First of all, I will explain everything. So I will deal with approximations to one number. Even if we approximate one real irrational number, there are still interesting and sometimes even exciting geometrical problems. I do not speak about difficult things, about transcendence theory and so on and so on. Just in geometry of approximation to one number, continued fractions, there are some interesting unsolved and sometimes more, sometimes less difficult problems. So one of them will be related to coprime approximations. Then I will speak about Minkowski function. We can go back for 100 years ago and recall the definition of Minkowski function. I will speak about exponents of growth, approximation constant, Diophantine spectra. I am a little bit afraid to speak now about Diophantine spectra because half a year ago I had lectures here in Chingo, and I discussed some open problems there. Maybe half a year passed. Maybe I don't know the current stage of the problem. Okay, let us think. And also, I will speak about Schmidt's problem about angles of inclination. And for each of this particular problem, I will give a brief survey of related results. So let us begin. So every Diophantine approximation lecture should start with Dirichlet's theorem. So what is Diophantine approximation? We want to approximate alpha, say irrational number by rational. So I will draw a picture. I will try to speak in a very, very simple manner because it may give an opportunity for people, even for younger people to understand what I'm speaking about. Also, I will formulate problems in a simplified way. So in the maybe very simplest cases of the setting. So, okay, we draw R2. I don't know, well, I don't know. We may consider this is a R2, or we may consider that here is M, and here is N, and here is a linear subspace of dimension M. But for simplicity, in the simplest case, M equal N equal 1. For the beginning of the lecture, it will be enough. And we are looking for integer points. We are looking for integer points, Q, P, which are close to this one-dimensional subspace. So this distance is just the difference. And the easiest and the first result here, if we look for hyperbola, so what is it? It is y is equal alpha x plus minus 1 over x. Then inside this hyperbola, we have infinitely many integer points, provided that alpha is irrational. This is a very simple statement, Dirichlet's theorem, which can be proved, for instance, by Bock's principle. And in fact, I did not write this slide, but theorem states something more. It states that in any parallelogram of such a type, for which vertex belong to the hyperbola, in any such parallelogram, there is an integer point. Well, so here I put coprime condition, but in this setting, it is absolutely clear. It is absolutely clear that if we have an approximation, then we have a coprime approximation, because if we have an integer point and this point is not primitive, then here we have another point which is primitive and everything is clear. So, but, well, let us go to a more serious setting. Before going to my first story, I will recall the simplest inhomogeneous setting. So instead of linear subspace, this is linear subspace. Subspace. Instead of linear subspace, we may consider affine subspace. It is y equal alpha x minus eta. And then we can catch integer points close to this subspace. But then, if we consider inhomogeneous approximation, then this argument with non-primitivity doesn't work. And it happened that by some reason, long, long ago, Erdős formulated a problem to understand to give a result in inhomogeneous approximation. Here we look for Q and R integers such that this inhomogeneous linear form is small. So to find inhomogeneous approximation of the best order of approximation. What is the result for coprime Q and R in homogeneous setting? And Erdős and Chok gave a certain answer. It is on my next slide. Oh, it works. Look. This easy and beautiful theorem says that this order for inhomogeneous setting is not enough to catch an integer point, in inhomogeneous setting close to this affine subspace. So here we have shifted hyperbola. To catch point here, to catch this point, we should increase the value of this difference. We cannot use 1 over q. We should increase it by this value with double logarithm. Honestly speaking, as many results, this theorem was forgotten. In last decade, people reproved weaker results. But when this theorem was discovered by Martin Widmer, I was able to prove a lower bound to construct a badly approximable number, a badly approximable inhomogeneous form with respect to this setting. But of course, there is no optimal result in order. There is a gap in order, and this is the first problem which I want to formulate during this lecture. So, I do not believe that it is possible to get an optimal order in this problem very easy. I will explain why. But I believe that it may be not difficult to improve these bounds and to get better results. Why I do not believe in an immediate optimal result? Because this problem is related or motivated by a difficult problem from analytic number theory, a problem of behavior of so-called Jakob-Stahl function. What is Jakob-Stahl function? Oh, look, let us solve the following problem, which is very popular just for students. If we have how large may be a sequence of successive positive integers which are not prime. If we put n equal k factorial, then it is an easy exercise that n plus 2 and so n plus k are not prime, are composite. And because this means that k is equal in order log n over log n, then Jakob-Stahl function sometimes is greater than log n over log n. So this is an easy exercise for pupils in secondary school. But if we look for, if you ask a question for the exact order of Jakob-Stahl function, so here is a original conjecture, and we see that it is in some sense far from solution, because upper bound belongs to Henrik Ivanets, and it is rather old, so, and nothing better is known since that time. And a lower bound, an improvement, was recently, and it was done recently, and it is related to a famous breakthrough in a problem of gaps between successive prime numbers. So, and the gap between upper and lower bound here still exists, and probably it is a difficult analytical problem. However, if we deal with my Diophantine problem, what is this? How? Oh, it works. It works. I wanted to turn back. If we deal with our Diophantine problem relates not to Jacob-Stahl function itself. It is related to multidimensional, say, two-dimensional generalization of Jacob-Stahl function, and two-dimensional generalization. The problem related to two-dimensional generalization is in much less developed stage. We know only almost trivial results, not easy, but not almost trivial results, but by Erdős from 50s. So if we consider, so here in this setting, we need to catch a box which contains of non-primitive points. And if x is the beginning of the box, then we are interested in the length of this box, which ensures primitive point inside. It seems to be that after easy results by Erdős, up to now, there is no other results. So there is a chance to do something here and to apply this to the Diophantine problem. So what can I say? Erdős proved two simple theorems. The first theorem gives a size of a box which contain only non-primitive points. And this is a simple application of Chinese remainder theorem. And the second result, which gives a larger box which contains primitive point, is related to extremely easy sieving. So, honestly speaking, these results do not contain analytics. So there is a chance for mathematicians to do something better. And there is a chance to do something better in the Diophantine setting, although the Diophantine setting is not related only to Erdős theorems. It includes some Diophantine construction, some construction with lattices, which also may be not optimal. So this is my first story. My second story, as I promised, is related to Minkowski. It goes back, so there is a tradition to have international congresses of mathematics, of mathematicians. So long ago, more than 100 years ago, there was also an international congress of mathematicians in Heidelberg. And there, Hermann Minkowski gave a lecture entitled On Geometry of Numbers. And during this lecture, what is geometry of numbers? Well, it is some kind of a kingdom which discovered to get Hermann Minkowski. Hermann Weil wrote, compared him with Bible, with King Saul from Bible, who also at the beginning of his career was not rich, but get a kingdom. Well, so, and in this lecture, besides geometry of numbers, Minkowski introduced Minkowski function. That time, just few decades ago, or just recently, that theory appeared. Cantor's approach came to the world, and Minkowski function seemed to be something strange. That's why he used this, roughly speaking, non-mathematical notation question mark function. After Minkowski, it was rediscovered several times. What is question mark function? So if we write here two numbers 0, 1 and 1, 1, we can define Minkowski from 0 is 0, Minkowski from 1 is 1, and then if we have two numbers, coprime, then we can define Minkowski function of its mediant as simply the mean value of the neighbors. So this formula gives an alternative definition. Here I wrote a definition in terms of distribution function of Stern-Brackel sequence. On my next slide, I will explain what does it mean. Now I will just I will just say that as it is asymptotic distribution function, it is clear that it is monotone. Continuity, you should prove continuity. It is easy. So I would like to recall a theorem which Lebesgue called his best one. So if we consider a monotone function, then almost everywhere it has finite derivative. This is one of Lebesgue's theorem, and he was very proud of this theorem. And because this function is monotone, it has a derivative, finite derivative almost everywhere. Salem proved that this function is singular. Derivative is, if exists, it is equal 0 or plus infinity. So by Lebesgue, almost everywhere the derivative is 0. And this phenomena in times of Minkowski was rather strange. That's why we have the following notation. Now I will draw a picture for Minkowski. So look, this is 1, this is 0, here it is 0, here it is 1. It is an easy exercise that in 1/2 it is 1/2. And important fact that if x is rational, then the derivative is equal to 0. So function behave itself something like this. And here I will draw y equal x. And by continuity, we have two extra stable points, which are written on my next slide. Oh, here I before extra points, I promised you that I will recall what is Stern-Brackel sequence. So here I gave the definition in terms of mediant. On my previous slide, I wrote that it is distribution function, but I didn't define what is f. I put it on my next slide. So here, how we can you can see Fourier tree. What is Fourier tree? How to get all rational numbers? You should take in the interval 0, 1. We should take 1, 0, 1, 1, 1, and then take medians from neighbors. So if you add numerator to numerator, denominator, you will get 1/2. Then if you take here, you will get 1/3. If you have here neighbors 1/3, it will be 2, 5, and so on and so on. So the nth level of this, yes? Wait a little bit. This is called Stern-Bracot sequence. I will mention Fourier sequence in my next slide. Look, very good questions, but I prepared an answer. So Stern-Bracot deals with binary tree. You see, if we come from here, root, here, then next one's binary. Stern-Bracot stops when we have the nth level of the binary tree. If we are interested in another problem, if we are interested in the problem to collect all numbers with denominator less than q, we should take boundary in a different way, not here, but boundary will take numbers from different levels of the tree. And this difference is of importance, and it is related to another problem, which I will speak a little bit later. So let me finish with stable points, and then we will see the difference between Stern-Bracot and Fourier. So, because, look, this is a folklore problem. In some, once upon a time, I read a text where it is declared that there are only 5 solutions of the equation question mark equal to x, but it is an unsolved problem, and up to now it is not clear what to do with this problem. So here I just proved existence of x1 and x2 by continuity and property of the derivative in rational points, this and this. Computationally, there is a computational evidence that there are no other integer points. But it is still an open problem. I want to mention a result of my students. They were able to reduce this problem to this nice Diophantine inequality. If this happens, so Minkowski in rational points is not close to x. It looks like Legendre theorem about convergence. So if this happens, then the conjecture is true. You do not have any other stable points. I think I know many people who tried to finish the proof of conjecture after they saw this statement. But nevertheless, this is still an open problem. And I wanted to tell you another open problem related to Minkowski function and related to the difference between Minkowski, between Stern-Bracot and Fourier. Look, I'm sorry, this slide contains much more formulas than previous one. It may be not very convenient, but what can I do? So, look, here is Stern-Bracot sequence, which we have discussed in details. But if we restrict denominators and pick up from these 3 numbers for which denominators are bounded, I did not write here q, I should write q. So it is not 0, it is q. So all the rational numbers with denominator bounded by q. we write it in an increasing order, it will not be the nth level of the tree. It will be something else. But you are able to consider distribution functions in both settings, for the tree and for Fourier sequence. For the tree, for Stern-Bracot, this function is Minkowski question mark function, something strange, at least for Minkowski times. But for Fourier tree, it is very natural. Fourier sequence is uniformly distributed. So distribution function is just x. Then we consider deviation. What do we do? We have an interval 0, 1. And we divide this interval into equal subintervals of length 1 over phi. This phi may be the number of elements from Fourier sequence, Fourier series. We use old terminology. They call it Fourier series, although it is sequence. Or from Stern-Bracot. So this is the number of elements in Stern-Bracot sequence. This is the number of elements in Fourier sequence. And we consider these sums. In fact, these sums are integral sums for the following integral. So you see, here we have a square of difference. Here is a regular net. Here is a natural net. Natural net for Stern-Bracot or natural net for Fourier. So being divided by the number of elements, this is an integral sum for these two integrals. The first integral is trivial, is 0. The second integral is non-trivial because here we have some components. We have non-zero area here. Okay, well, and so Fourier is something classical. If we look into famous book about analytic number theory by Landau, we will find the Fresnel theorem, an equivalent formulation of Riemann hypothesis, which I was speaking about in the very beginning. So if we consider this deviation, it is O small from 1, and it is equivalent to prime number theorem. And this estimate for deviation is equivalent to Riemann hypothesis. Now the problem. What is an analog of Fresnel theorem for Minkowski function? I don't know any reasonable answer. I was able to prove by myself, it is an easy statement, a corollary of Cox's inequality, that this deviation, of course here we do not have zero main term because the integral is not 0. But if we consider deviation, so here we have the main term integral. If we consider remainder, it is not difficult, almost trivial to prove that this remainder is less than 4. 4, what is 4 here? 4 is a total variation of this function, question mark minus 6 square. If we write it without brackets, you will have 4 summands, and this is that 4. So this is Cox's inequality, and we do not know any other result. So compared to classical setting with Fourier sequence, in non-classical setting, we do not have even an analog of prime number theorem. So prime number theorem claims that it is O1. And here we have O capital O1. So this is the end of my story related to Minkowski. I will continue with some other stories. What is next? This is, it is previous, sorry. Okay, fine. Next, again is related to one-dimensional approximation. No, to higher dimensional approximation. I recall very well-known famous theorems, and I think here in China that they are even better known. Well, look, if we consider convergence to continued fractions, it is absolutely clear that they have exponential growth, and the smallest exponential growth is related to golden section. It is obtained on golden section. It is just a corollary of recurrence inequality for denominators. And if we consider mean value theorem, there is a nice ergodic theory, a nice ergodic theorem by Levy, who proved that for almost all alphas, we know the growth of denominator, it converges to this exponent. Well, now I want to speak about multidimensional situations. So next problems which I will speak about will be multidimensional, and best approximations is a very, very good tool to produce multidimensional generalization of continued fractions. Because, so, if we consider convergence by Lagrange theorem, convergence are just best approximations in that sense that if we have the value of linear form where close to this subspace, where we have no other integer points, these integer points are just the points which correspond to numerators and denominators of continued fraction. And this definition can be easily generalized to higher dimension. Oh, no. I'm next to higher dimension. To higher dimension. But in higher dimension, we have different definitions with respect to different norms. We can evaluate the closeness of a point to a line. So I consider a section. We can consider arbitrary norm, and each norm leads to its own sequence of best approximations. As usual, we use here norms subnorm or Euclidean norm. But in each of these norms, we can consider the sequence of best approximations, and I'm happy to mention a metric result, an analog of Levy's theorem, which was obtained quite recently by one of our hosts, Itwok Chung, together with Nikolai Chevalier. So they were able to generalize this statement for higher dimension. So in metrical setting, we can say that we know everything. There is a constant. They have a special paper devoted to calculations of this constant. So it is explicit constant, which says that, well, for almost all alphas, we know the exponent of growth. But I'm more interested in an extremal problem. What happens not for almost all numbers, but for all numbers? What is the lowest order of growth? Well, this problem turned out to be not so easy. Because let me not explain why, but let me just simply give a brief history. Some time ago, in dimension 2, Lagarius conjectured that the lowest exponent of growth is related to the root of this polynomial. This is a very nice polynomial who has one real root and two complex roots. In the corresponding extension, K, which is Q from 3 theta, we have one real field and two complex conjugate field. We have just one Dirichlet unit, and the dynamics generated by a group of units in three-dimensional space is very easy. We have just rotation by spiral, which converges to one axis. So that was the argument I guess, I don't know. I don't know logarithm. I think this was the argument why he suggested that he conjectured that this is the optimal bound. However, it is not still proved. Moreover, I have a feeling, I'm not completely sure, but I have a feeling that even in the simplest case, when we deal with simultaneous approximations to theta 3 and theta 3 square, so we are interested, what is simultaneous approximation? We have R3, we have one x and two y's. We have line here, y1 equals theta 3 x, theta 3, was it? 1, 2, y2 is equal theta 3 x square, and we are interested in finding best approximations to this line with respect to Euclidean norm. So we are looking for integer points in cylinders which surround this line. Even in this case, I think a proof of the statement that the exponent of growth of best approximations is determined by this constant has never been published. Moreover, I am not completely sure that it is really so. Probably it is so, but I'm not completely sure. Even in this example, and for subnorm and for Euclidean norm, we have only Itva, you're in time, almost in time. Glad to see you. So, well, but in Euclidean norm and in subnorm in two-dimensional case, we do not know extremal values. These very partial tiny results I mentioned here just to show that there is a lot of opportunities to prove not everything but something. This result in subnorm is done by hands. This result in Euclidean norm is done by computer who worked for several days. And what I can say, of course, exponential growth of best approximations in principle is easy. In principle, it is easy to prove some bounds. And in general case, I know only bounds related to Kissing number of the unit ball in the corresponding norm. What does it mean? Related to the following simple observation. If we have best approximation, then the next best approximation cannot lie in a shifted ball in the corresponding norm. So the exponent of growth can be bounded in terms of Kissing number. Kissing number, it is the number of balls, of unit balls, which can touch a particular unit ball. So, okay, I think I'm continuing. I have some more stories. I promised 6 stories, but I told you only 4 stories. Next one. Oh, next story is about the Diophantine constant. It is a very funny story. Please have a look. So when we approximate one number, we have this square root of 5 as an approximation constant, and it is optimal because if we take golden section, the continued fraction with all ones, then we have the opposite bound. I mean that for golden section, if alpha is square root of 5 plus 1, then for any epsilon, if we consider this inequality has only finitely many solutions. Oh, I wrote it in a linear form. Q alpha minus p is less 1 over plus epsilon here q, only finitely many solutions. This constant is optimal. And I will consider now only case of simultaneous approximation. We are interested in getting optimal constant in this setting when we approximate. Oh, I wrote here subnorm. Maybe I am not right. Why? Because the only solved case, the only case where we know and the exact solution is very old case of Euclidean norm, which was done by Mahler and Davenport, which is related to square root of 23. I can ask question where in my previous slide this square root of 23 appears. It appears in a non-explicit form somewhere. I will not answer. Okay, so this constant is optimal, and there is an algebraic lattice for algebraic number for which this constant is obtained. And for subnorm in two-dimensional case, we do not know optimal constant. We know only bounds, old bounds by Castles, and a relatively new bound by Werner Georg Nowak, who has a lot of results in lower dimension. And in fact, he discovered one more three-dimensional body for which we know definitely critical determinant. This is, we know critical determinant for very, very few collections of three-dimensional points explicitly. So, this is what I can say with respect to two-dimensional case. But if we deal with asymptotics in dimension, we have a very funny story. I am passing to this story. So now we are interested in subnorm. We are interested in subnorm, and we are interested in this constant, and we want to have this constant as better as possible. It is convenient to write this constant here in brackets, so 1 over n. Why it is convenient to do so? Because if we use Minkowski, then we will get E as a constant. There was a story of improving this constant, which after Minkowski started with Blickfeld, E plus 1 over E. Then time passed, there was a variational problem, which was completely solved by Spohn in 1967, who replaced E by pi. Then the science mathematics stopped. And after this pi, up to now, there was nothing. Just almost nothing, because there were very, very tiny improvements by me and Nowak, which do not improve pi. They improve a little. They say that pi is not optimal. But the problem is that this result, Spohn's result, is related to solution of a variational problem. He reduces multidimensional problem, n-dimensional problem, to two-dimensional problem. And he gives an exact solution of a variational problem in dimension 2. But best approximations in higher dimensions do not have symmetry, do not have isotropy. So the directions are of importance. No results here use non-isotropy. So they use arguments similar in any direction. That is why, of course, these results are non-optimal. And it would be very nice if somebody will prove a result here with constant which goes to infinity. So lower bounds, so to improve lower bound essentially, instead of these improvements, instead of pi, to get something which goes to infinity would be very interesting. By the way, upper bound here is very, very large. Is of factorial growth. Now, next problem I wanted to speak about, I still have some time, and this is wonderful. So next problem is related to Diophantine spectra. This is to deal with my next problem. It is more convenient for me to deal with irrationality measure function. What is irrationality measure function? So we simply consider best approximations, relative minima of this form. So irrationality measure function can be drawn in the following way. So you have t, here psi t. It is a piecewise constant function. So I had the lectures here in winter, and each lecture I draw this picture. So these are just convergence. Convergence I expressed on this slide. There is a nice formula which is called Perron's formula, and which helps to analyze the behavior of objects from my next slide. So you need to consider the following objects: t times psi t alpha. This is the areas of these parallelograms. This parallelogram, in the case of lim sup, this is for lim sup. And for lim inf, we need to consider smaller parallelogram. This is lim inf. This is for lim inf. And the possible values of these limits are well known as Lagrange constant and Dirichlet constant. So Lagrange constant, this is a famous story that the set of all Lagrange constant forms so-called Lagrange spectrum. This is a discrete part discovered by Markov. This is a whole complete interval, which was existence proved by Hall, and this constant is due to Gregory Freeman. This is another story. I have no time to speak about this. But if we deal with lim sup result with Dirichlet spectrum, this constant, this is Hurwitz, and this is by Sekeres. By the way, for a long time we thought that this should call Schmidt-Davenport constant, because they reproved Sekeres result sometime later. But this discrete part is due to Morimoto and Liska. And by the way, ray was proved by Boguslav Divich. He was a student of Yarnik, and it is a very strange thing, because for Hall's ray we know a lot of results, and we even more or less know the optimal H. And here we do not know optimal Z, although Dirichlet problem is much easier. So each of my slides was a separate lecture, but I'm passing to the next one. Now, what I have said. So I am speaking about the situation which was this winter. Maybe something changed. If we deal with multidimensional approximation, simultaneous approximation to two numbers, we do not have continued fractions. So for the previous result, it is terrible, but for the previous result, everything is proved in terms of continued fractions. We have no argument without artificial isolation based just on compactness. No argument. That is the reason why we have nothing reasonable for Lagrange spectrum in dimension 2. In any norm, we do not know if there exists a whole ray in spectrum. We even do not know if L2 is uncountable. So open problem, open problem, L2 uncountable. It is terrible. It is absolutely clear that L2 is uncountable. But we do not have a proof. The only thing, the best result I know, is due to my student Akhundjanov, who proved that for every epsilon, there is an element of Lagrange spectrum between epsilon and epsilon. I'm not sure that you can prove here 5, 2. I think you can prove 2, 4, 2. You can, I think you even cannot prove 4, 2. I think you will prove 4, 2. I think what we discussed in winter means 4, 2. But Akhundjanov can get 5, 2. So, but it is nothing, because it does not give even uncountability. So it is very, very, very weak result. So we should say indeed, we know nothing. So, and well, I still have half a minute. So I wanted to tell you 6 stories. So about the 6th story, I will say just that the 6th story does exist. It is related to for higher dimension. There is a story that for Dirichlet spectrum, it is very strange, but for Dirichlet spectrum, everything is known. For Dirichlet spectrum in higher dimensions, everything is known. It was discovered by Akhundjanov and Shaskov, but they were lazy. They dealt only with the case of Euclidean norm and dimension 2, and in higher dimensions, quite recently, a general result was announced by Barak Weiss and Alon Agin. It was announced at the last conference in Diophantine Approximation. So half a word about 6th story. 6th story is devoted to approximation by angles. And there is, if we have a irrational subspace, we want to approximate it by rational subspace in terms of minimal angle between these subspaces. And quite recently, there was a dramatic story related to a result by Elio Joseph. So this is too complicated formula for our lecture. I skip it. So we deal with approximations of 2-dimensional subspaces by 2-dimensional irrational subspaces. Schmidt proved the following result, that this is analog of Dirichlet's theorem. For any irrational subspaces, there exist infinitely many rational subspaces with such angles in terms of height of the subspace. And it turned out, surprisingly, that this exponent is optimal. It is a breakthrough result of Elliott Joseph, who constructed a simple but very artificial subspace, which has no approximation by rational subspaces. By the way, this construction is related on one of the solutions of Schmidt's bed conjecture from Schmidt's paper. It is related to Beresnevich theorem on badly approximable numbers on curves. But it is very likely that this is an answer for particular approximation, but metrical exponent should be 4. So we have in metric number theory, we have convergence divergence theorem. And the convergence theorem here is easy. So it was proved some time ago. Unfortunately, up to now, we're not able to prove divergence result. Maybe Nikolai Moshchevitin will do, because we discussed something with him. So unfortunately, the last story was very, very pressed. So I do not have time to speak more. But there is a lot of other different stories, other different more or less unsolved problems. I would like to finish with the words, my lecture with the words by Henri Poincaré, who said that there is no solved or unsolved problems. There are problems which are more or less solved or more or less unsolved. So thank you very much. So I have one more slide.
Thank you very much for many interesting problems. So any question for the audience?
I have a question about the second slide of the second story. Just about the Stern-Brockhaus sequence.
What? Sorry, what?
Just about the Stern-Brockhaus sequences, FN.
Bounds for. Stern-Brockhaus, yes. Stern-Brockhaus, yes.
I wonder that the number just added into the next Fn is the rational number such that it has the least denominator between the two numbers of the last one.
Stern-Brockhaus sequence is a tool to construct, maybe considered as a tool to construct continued fraction. For instance, if you have, as far as I understand, you are speaking about, so you have alpha, and you need to, you want to construct successive nested intervals from Stern-Brockhaus sequence. What do you mean?
For example, the number 2 divided 5 in F3 is the rational number such that it has the minimal denominator between 1/3 and a half.
Here.
Yes. So does each number in that sequence has this property?
Roughly speaking, if you have two neighbors, then CD minus AB is 1 over BD.
I thought this is a trivial property of the series.
Yes, I think so. This is just follows from the construction by induction.
How do you prove it?
It is very simple by induction. So if we have AB minus CD equal to 1 BD, here we include A plus C, B plus D, and you can AB CD this determinant write as A plus C, B plus D, CD. These determinants are equal, and this is an inductive step. Okay, this is very easy.
Okay, I think we should stop now. If you have
Yes.
ask the professor privately. Okay, I guess we should start next talk. It's already a little late.